Hello everyone. As discussed in the introductory session, we all know that power consumption is a very huge challenge in a modern day VLSI design. Reduction in power consumption makes a device more reliable. In this particular session, we will discuss the basic concepts of power and the types of power dissipation. Also, we will discuss the various sources of these power dissipation in the coming modules in detail. So let's start this session. In today's module, we will discuss the basic concepts of power, the power consumption in CMOS circuits, dynamic power, static power, the power challenge, and conclude the session. Power terminology. Power is the rate at which energy is delivered or exchanged. Basically, we say that electrical energy is converted into heat energy during operation, that is the active mode of the device. Now, how can we distinguish between the power consumption and the power dissipation? The power consumption probably refers to the power input to the device which is under consideration. So we can say that it is the power taken by the device for its operation. And power dissipation refers to the losses associated with the device that are dissipated as heat, or we can say that it indicates the amount of power wasted by a given device. Or in other words, we can also define it as rate at which energy is taken from the source, that is the VDD, and then it is basically converted into heat. Now, we can also classify the different types of power. First, we have the peak power. When we plot the power dissipation of a circuit over a period of time, this is the power which is the function of the time. So this is the peak power. Okay, as we can see, it refers to the maximum power drawn by the circuit. It is not a constant value. Sometimes it is more or less. So we say it is a function of time. This type of power occurs in many situations. For example, when you are turning the power of a laptop or a computer, then at that point, it will consume a large power, or we can say the maximum power. Whenever there is a surge in power dissipation, that means suddenly a power increases, then also we define it by the peak power. Also, the term power leads to the term energy. So we associate it with the energy also. Next, we have the average power. Average power is basically the average of the instantaneous power dissipated over a period of time t. Suppose we have a time period t as seen in the graph. So we will calculate the average power because sometimes we may have peak value, sometimes we may have smaller value. So we generally take an average and then we calculate the average power. Now, next, when I say that power can also be associated with the term energy, so basically energy is the most important parameter, okay? And energy actually defines the consumption of this device for its working. Now, how can we define or how can we tell the definition of power and energy by the help of the formula? So here we have the VDD, that is a constant source of the voltage, or we can say the supply voltage. And I over here shows the current. Okay, so instantaneous power will be given by the product of the current and the voltage, that is IDD into VDD. Then we have the energy, which is integrated. Instantaneous power is integrated over a period of time, that is 0 to t. And the average power is calculated, that is the energy over a period of time, average of all the values. So we'll basically divide it by the time period t. Now, figure of merit, or we can say how we tell the performance of any particular device. So figure of merit is basically the product of the signal propagation delay times and the average power dissipation. Okay. For digital systems, we are considering PDP, that is the power delay product. It is a quantity which is used as a measurement of effectiveness of a system. Okay. So if we say power consumption in watts, it basically determines the battery life in hours. Then we have the peak power, which determines the power ground wiring designs. It is used for the setting of the packaging limits. It also impacts the signal noise margin and the reliability analysis. If we are defining the energy efficiency in joules, then it means the rate at which power is consumed over time, which we have already discussed in the previous slide. So basically, you need to remember that figure of merit for digital systems or for the VLSI devices, we can say it is power into delay. That is, joules is equal to watts into seconds. Okay. Lower energy number means less power to perform a computation at the same frequency. Now, how we classify the source, or we can say the power dissipation can be classified into two types, the dynamic power and the static power. In simple words, we define dynamic power, which is consumed by the circuit when the circuit is in the active mode, and static power, it is the power consumed by the circuit when it is in the standby mode. Now, how we define the power consumption in integrated circuits. So each IC consumes some power for its operation. It is again divided into static power and the dynamic power. The sum of these two tells you the total power consumption or the total power consumed by the IC. Okay. Now, how we will compare both the power, that is a dynamic power versus static power. Now, dynamic power means when there is a switching between the logic gates, okay? And static power means when the circuit is not working, but still some leakage currents are present. Due to that, we are having power dissipation, okay? Again, dynamic power is associated with active mode and static power is associated with the standby mode as defined in the previous slide. In dynamic power, we have two components. It is divided into two parts, the switching power and the short circuit power or the internal power. Then we have in static power only it is because of the device shrinking, or we can say because of the leakage current. Okay, the static power is because of the leakage current. Now, types of power dissipation in CMOS. How can we define CMOS? Let's take example of CMOS inverter. Here we will define various types of power dissipation within the circuit. The dynamic power dissipation is because of the input-output switching activity. Then short circuit power dissipation is because when the NMOS and the PMOS both are on during some duration of time, and there is a short circuit path between the VDD and the ground, during that short circuit current flows, which is shown by the ISC. That is called as the short circuit power dissipation. And this static power dissipation is basically because of the leakage currents present in the device. And when the circuit is not working, that time also we are experiencing some power dissipation that comes under the category of the static power dissipation. So these three types of power dissipation are basically occurring inside the CMOS designs. Now, when I say dynamic power, how it can be shown by the help of the formula. Here, dynamic power dissipation is a function of capacitance, that is a load capacitance. Then we have the supply voltage, square of supply voltage. Then we have the activity factor. Here, activity factor means the switching between the inputs from 0 to 1 or 1 to 0. And F here shows the clock frequency. So these are the basic parameters which can be defined in the dynamic power. Then the short circuit power, like I already told you, during a transition, when both the transistors are on, the PMOS and the NMOS, there is a current flows simultaneously for a short period of time. The VDD and the ground are short circuited. And this current, which is flowing from VDD to VSS, is called as the crowbar current. Okay. And the third type is static power dissipation, which is the leakage power is resulting from the leakage current present inside the transistors. And we can just give it by the formula, that is VCC into ICC, that is the supply voltage and the leakage current. Okay. So V into I. And for any IC, these are specified in the data sheet, which is provided by the manufacturer. And for the static devices, for the CMOS devices, the static power is very low, almost equivalent to 0. But as the technology shrinked and the device size reduced, the device miniaturization came, this leakage component became dominating over the dynamic component. And the leakage currents started increasing, and the overall static power dissipation increased. Different types of leakage current are present, like drain junction leakage, subthreshold leakage current, the gate leakage current. All these types of currents will be discussed in the next module in detail. Now, if we calculate the average power consumption of all the three types, it is actually, we can say, for the conventional CMOS circuit designs, which were designed earlier when the scaling was not up to that level, the static was less than 1%. And the short circuit power dissipation, or the dissipation due to short circuit current was approx to the 10%, and the major component leading to the power dissipation was the dynamic power dissipation. Okay. Now, as the technology shrinked, or we can say the scaling was introduced, and the sub-threshold leakage current increased, it became the large component of the total participation. So we can see through the graph, as the device dimensions are reducing, that is, it is going into nanometer and reducing day by day. The power component, we have the leakage component is increasing as compared to dynamic over the years. So we can basically conclude that power dissipation in static is because of the three components: the dynamic, that is the capacitive, majorly the switching activity, the charging and the discharging of the capacitor. Then we have the crowbar current, that is the short circuit part. The current flows because the P and the N transistors are on for a short period of time. And third type is the leakage, that is the current due to the leakage mechanism, or we can say the different types of defects introduced because of the scaling. And it majorly produced when the circuit is in the standby mode. So thank you for attending this session. In the next session, we will discuss different types of dynamic power and the static power dissipation in detail. Thank you.